This is the Physics 1 Lab 1 report covering constant velocity and its relation to the fundamental physics principle Newton's second law. An object is recorded moving at constant velocity, analyzed using the software tracker, and a model is created using GlowScript to predict the object's motion. Also used in this experiment is Newton's first law, which states that an object in rest remains at rest and an object in motion remains in motion at a constant velocity unless acted upon by an external force. Newton's second law states that net force equals change in momentum over change in time. At constant velocity, net force is equal to zero. The velocity update equation derived from Newton's second law demonstrates this because for a velocity to remain constant, v final must equal v initial. This means that the term F net over mass times delta t must equal zero, but delta t is not zero, so therefore F net has to be. This lab demonstrates how using Newton's second law rearranges the velocity update formula, iterating it multiple times and choosing a small delta t can lead to very accurate predictions of an object's movement at constant velocity. The position update formula shows how the average velocity relates to an object's position at a certain time. In the GlowScript code, the velocity from the iterated velocity update formula in the while loop is used as the average velocity term in the equation. To find the initial velocity used for the GlowScript code, I simply took the second position vector recorded in tracker minus the first over the change in time over that interval. Iterating Newton's second law gave a relatively strong prediction of my experimental results. In my experiment, the system, or the object of interest, is my soccer ball. The surroundings are everything outside of the system that can interact with the system. Some examples of things in the surroundings are the earth, me, and my mom. Tracker requires a known measurement for calibration, so I used the diameter of the soccer ball. The coordinate system I chose was standard, with positive x to the right, positive y up, and positive z toward the camera. Here is the tracker ball moving in constant velocity. Since I chose the coordinate system I did, the ball was moving in the negative x direction. Moving on to the GlowScript coding, here are the initial conditions I entered. The mass of the soccer ball is 45 grams, or 0.45 kilograms. I used the initial position from tracker at negative 9.173 times 10 to the negative 4th meters on the x-axis. I used the initial velocity equation and subtracted the initial position from the second, then divided that number by the change in time. The initial velocity came out to be negative 1.28 meters per second. The initial time was 0. Since the velocity update formula works best with a small delta t, I chose 0.01 seconds as mine. This does not have to match with the intervals in tracker. The end time from tracker is 1.033 seconds. This is plugged into the conditions of the while loop. Since the velocity is constant, I plugged the zero vector in as F net. The while loop in this code essentially iterates Newton's second law and updates the wall's velocity and position each delta t. The velocity update and position update formulas are in the while loop to do this. After running the code, I can see that my model was a pretty good prediction of the movement of the soccer ball. Watching each video back to back, I can see that the motion is very similar. Looking at the graph, the experimental data is indicated with the magenta dots and the model indicated by the blue line. They start off very close, however, they start to separate a bit more near the end. There are 2 data points at the start of the experiment that are relatively horizontal to each other, and 3 at the end. This is because the ball was relatively at rest for these frames, but since the model starts at time equals 0, it doesn't take into account this lack of motion. The code continuously iterated Newton's second law, which kept the velocity the same as the initial since F net equals 0. The initial velocity I used was derived from the first 2 data points. This may not have been entirely accurate for the whole experiment, which could have thrown the model off as well. Overall, however, it is a relatively good predictor of the ball's experimental results. What if I had chosen a different coordinate system in tracker? Since vectors are made of direction and magnitude, the magnitude would not change based on the coordinate system, but the direction would. For example, if I had flipped the positive and negative x directions in my chosen coordinate system, the ball would have traveled the same distance at the same speed, but in the positive x direction rather than the negative. What does it mean? Is it possible to say how many forces acted on the system to produce the 0 F net necessary for constant velocity? No, there is an indeterminate number of forces that can act on the system. There are many things in the surroundings that can interact with the system, and it is not possible to tell exactly what these things are or how many there are.